Are we truly alone in the vast expanse of the cosmos? This question has haunted humanity for centuries, sparking our imagination and driving our deepest curiosities about what might lie beyond our pale blue dot. For generations, we've gazed up at the star-filled night sky, wondering if somewhere out there, other eyes might be looking back at us. Other civilizations might be asking the very same question. That burning curiosity has evolved from mere speculation into one of the most thrilling scientific quests of our time, the search for habitable worlds beyond our solar system, places where life as we know it might not just be possible, but actually thriving right now. The journey to answer this profound question began with two revolutionary concepts that reshaped how we think about extraterrestrial life. First came the Drake equation, a fascinating mathematical formula that attempts to estimate the number of communicative civilizations in our galaxy. Then there's the Fermi Paradox, which presents a puzzling contradiction. If the universe should be teeming with life, why haven't we found any evidence of it? These two ideas have fueled both scientific inquiry and public imagination, creating a framework for understanding just how many worlds might be out there waiting to be discovered. They've transformed our search from simple wonder into a calculated, systematic exploration of the cosmos, using the most advanced technology humanity has ever created. Today, we stand at an incredible moment in history where we're not just theorizing about alien life, we're actively hunting for the worlds that could host it. Astronomers have identified thousands of exoplanets, and among them are 30 extraordinary candidates that have captured scientific attention worldwide. From mysterious water worlds with global oceans deeper than our imagination can grasp, to super-Earths with conditions that might be perfect for life to flourish, these distant planets represent the most promising locations we've ever discovered beyond our solar system. Each one tells a unique story about planetary formation, habitability, and the incredible diversity of worlds that exist in our galaxy. In this exploration, we'll journey through these 30 remarkable planets, uncovering what makes each one special and why scientists believe they might just be the places where we'll finally answer humanity's oldest question. Our journey begins remarkably close to home, cosmically speaking, with a world that orbits our very next-door stellar neighbor. Just over 4 light-years away, Proxima Centauri b offers the tantalizing possibility of an Earth-like environment right in our own cosmic backyard. This exoplanet holds a special place in the search for life, primarily because its mass is so similar to our own planet's, suggesting a rocky composition we would find familiar. But its proximity to its parent star comes with significant challenges. Proxima Centauri b is almost certainly tidally locked, meaning one side permanently faces its sun, basking in endless daylight, while the other is plunged into eternal frozen night. This creates extreme temperature differences that would make life difficult, though not necessarily impossible, as theoretical models suggest a potentially habitable band could exist along the twilight line between these two harsh realms. To make matters more complex, Proxima Centauri is a volatile red dwarf, frequently erupting with powerful stellar flares that bathe its orbiting planet in intense radiation, potentially stripping away any atmosphere and sterilizing the surface. Despite these formidable obstacles, its incredible proximity makes it a prime candidate for future study, a world so close that it ignites our imagination about what might be lurking virtually next door. Venturing a bit farther out, we encounter one of the most astonishing planetary systems ever discovered. 40 light-years from Earth, the TRAPPIST-1 system is home to not one, but 7 rocky worlds, all roughly Earth-sized, with 3 of them, including TRAPPIST-1e, orbiting comfortably within the star's habitable zone. This is the zone where temperatures are just right for liquid water to exist on a planet's surface, a key ingredient for life as we understand it. TRAPPIST-1e stands out as particularly promising. Its size and mass are almost identical to Earth's, and its density suggests a rocky composition that could feature a solid surface, continents, and perhaps even deep oceans. Because the entire system of planets orbits very close to its ultra-cool dwarf star, each world would appear large and vivid in the skies of its neighbors, creating a spectacular celestial dance. The potential for liquid water, combined with its Earth-like qualities, makes TRAPPIST-1e a compelling target in the search for biosignatures, atmospheric chemicals that could only be produced by living organisms. Rounding out our first look is a true pioneer in the field of exoplanet discovery. Kepler-186f, located about 500 light-years away in the constellation Cygnus, holds the historic distinction of being the very first Earth-sized planet ever confirmed to be orbiting within its star's habitable zone. This discovery, made by NASA Webb Space Telescope, was a monumental moment that proved planets like our own were not just theoretical possibilities but actual realities in the cosmos. Kepler-186f orbits a red dwarf star, much cooler and redder than our Sun, which means its habitable zone is much closer in. While we don't yet know the precise composition of its atmosphere, or if it even has one, its Earth-like size drastically increases the chances that it's a rocky world rather than a gaseous one. The mysteries surrounding this planet are profound. We can't say for certain if it rotates, creating a day-night cycle, or if it too is tidally locked. Yet, its existence alone is a powerful testament to the abundance of potentially habitable real estate in our galaxy, a world that expanded our understanding of where life might just take root. Shifting our gaze further into the cosmos, we come upon a world that feels hauntingly familiar. Kepler-452b, often nicknamed Earth's cousin, orbits a star that is a near twin to our own Sun, both in type and age. This remarkable similarity means the planet enjoys a yearly cycle of 385 days, basking in sunlight very much like our own. Its position within the habitable zone of such a stable, G-type star makes it one of the most Earth-like worlds we've ever discovered. The possibility of a rocky surface and a substantial atmosphere opens up the incredible prospect that conditions there could support not just liquid water, but even processes like photosynthesis. Imagine for a moment a landscape where the light from its sun feels almost identical to our own, potentially nurturing a similar kind of life. While it is significantly older than Earth and its greater mass suggests stronger gravity, the idea of a sunlit world so reminiscent of our own fuels the imagination about what might have had billions of years to evolve there. Our next destination presents a stark contrast, an example of a super-Earth that defies our terrestrial expectations. LHS 1140b is a massive, rocky world located about 49 light-years away, and it is a compelling enigma. Its considerable size and density suggest it could possess a substantial iron core, much like Mercury, but its true allure lies in what might surround that core. Scientists believe this planet could be blanketed by a tremendously thick atmosphere, one far denser than our own. Such an atmosphere would act as a powerful insulator, effectively trapping heat from its red dwarf star and potentially creating a stable, warm environment on the surface. This greenhouse effect could be so efficient that it might maintain vast, global oceans of liquid water despite the planet receiving less stellar energy than Earth. It presents a fascinating scenario where a world that might otherwise be a frozen rock is instead transformed into a possible water world, utterly dependent on its atmospheric blanket for warmth and stability. Completing this trio is a planet that offers a quieter, more peaceful alternative to the violent flares of its stellar neighbors. Ross 128b orbits a red dwarf that is notably inactive, a calm and stable star lacking the frequent, life-sterilizing eruptions that plague systems like Proxima Centauri. This tranquility is its greatest asset. Located just 11 light-years away, this temperate world, with a predicted surface temperature that could be remarkably mild, is considered one of the very best candidates for habitability in our entire celestial neighborhood. The absence of constant stellar radiation bombardment dramatically increases the chances that Ross 128b has been able to retain a life-sustaining atmosphere over billions of years. This combination of a calm parent star and an orbit within the habitable zone makes it a prime target for future telescopes, which will scan its air for the telltale chemical signatures like oxygen or methane that could finally reveal the presence of a living world. Moving further into our cosmic catalogue, we find a world that challenges our basic assumptions about where liquid water can exist. GJ357d is a super-Earth, a planet several times more massive than our own, orbiting a small, cool star located just 31 light-years away. While its parent star provides far less heat than our Sun, this planet's orbit places it right on the outer edge of the habitable zone. At first glance, that might seem too cold for liquid water. However, its significant mass could be the key to its potential. A planet of this size is likely to possess a very thick atmosphere, a dense blanket of gases that acts as a powerful insulating layer. This atmosphere could effectively trap what little heat it receives from its star, creating a potent greenhouse effect that warms the surface enough to maintain vast global oceans. This turns the traditional concept of the habitable zone on its head, suggesting that a world we might have written off as an icy rock could in fact be a shrouded, watery abyss, proving that habitability isn't always about location, but also about a planet's own internal and atmospheric dynamics. In the constellation Aries, a mere 12 light-years from Earth, orbits a planet that scores remarkably high on a very special scientific scale. Teegarden's star B boasts one of the highest Earth Similarity Index values ever recorded for an exoplanet. This index is a complex calculation that compares a world's radius, density, surface temperature, and escape velocity to our own planets, providing a numerical estimate of just how Earth-like it might be. Teegarden's star B doesn't just orbit within its red dwarf's habitable zone. It does so with a stellar flux almost identical to what Earth receives from the Sun. This means the amount of energy bathing the planet is strikingly familiar, a crucial factor for any Earth-like life forms. Furthermore, its parent star is an ancient, stable red dwarf, billions of years old, suggesting it has long since settled into a calm phase, offering a stable and consistent environment for an extraordinarily long time. This combination of Earth-like energy input, a stable star, and its proximity to our solar system makes it an exceptional candidate in the search for a true analog to our own world. Perhaps no planet on our list has generated as much recent excitement as K218b, a world located 110 light-years away that fundamentally expanded our idea of what a habitable environment can look like. This is a hycean world, a term blending hydrogen and ocean, an entirely new class of planet theorized to possess a massive, hydrogen-rich atmosphere enveloping a global liquid water ocean. In 2019, astronomers made a historic announcement. They had detected significant amounts of water vapor in the atmosphere of K218b. This was the first and only time such a discovery has been made on a planet residing within its star's habitable zone. The implications are staggering. A thick hydrogen atmosphere could create immense pressure at the ocean's surface, potentially preventing the water from boiling away even under higher temperatures. This environment, while utterly alien to us, might be perfectly suitable for certain types of microbial life, similar to extremophiles found in Earth's deep-sea hydrothermal vents. The discovery of K218b didn't just add another planet to the list, it blew the doors wide open, forcing us to consider that life could be thriving in conditions we never before imagined possible. Our journey now takes us to a world discovered by one of the most prolific planet hunters of our time. TOI 700d holds the distinguished title of being the very first Earth-sized planet ever discovered by NASA test mission, orbiting squarely within its star's habitable zone. What makes this planet, located just over 100 light-years away, so compelling is its remarkable stability. It completes an orbit around its calm M-dwarf star every 37 days, a predictable and steady rhythm that stands in stark contrast to the volatile flares of other red dwarf systems. This consistency is a boon for potential life, as it suggests a far more stable climate. Computer models of its potential environment present several fascinating possibilities. Some simulations indicate that TOI 700d could be a tranquil, water-covered world, its entire surface a single, global ocean with a dense, cloud-rich atmosphere. Other models suggest it might be a drier, land-dominated planet, yet still with regions temperate enough for liquid water to pool and flow. Its discovery by TESS not only confirmed the telescope's incredible capabilities, but also delivered a prime, stable target for the next generation of observatories to study in exquisite detail. Venturing into a truly exotic stellar neighborhood, we find GJ 667cc, a super-Earth that calls a triple-star system home. Imagine a sky where not one, but 3 suns grace the heavens, a breathtaking spectacle of multiple light sources and complex orbital dances. This planet, roughly 3.5 times more massive than Earth, orbits the smallest star in this trinary system, which itself is located a mere 22 light-years from us. Despite the apparent complexity, the 2 other, brighter stars are actually far enough away that they would appear simply as exceptionally brilliant stars in the sky, not as additional suns providing significant heat. This means GJ 667cc receives a similar amount of energy from its primary star as Earth does from the Sun, placing it firmly within the habitable zone. Its substantial mass strongly implies a rocky composition, and while it may be tidally locked, the potential for a thick atmosphere could distribute heat effectively around the planet, potentially creating a wide range of environments where life could find a foothold beneath its triple-sun sky. Finally, we revisit the legacy of the Kepler telescope with a look at a world that helped redefine the outer boundaries of possibility. Kepler 62f is an exoplanet of profound significance, orbiting a star much cooler and smaller than our own Sun, about 1,200 light-years away. Its year is 267 days long, a stately and slow journey that places it on the cooler, outer edge of its star's habitable zone. This position initially led to questions about whether it might be a frozen, icy world. However, its size, only about 40% larger than Earth, makes a rocky composition highly probable, and the potential for a substantial atmosphere changes everything. An atmosphere rich in greenhouse gases like carbon dioxide or methane could act as a powerful insulating blanket, trapping enough stellar energy to warm the surface to temperate levels and maintain liquid water. Kepler 62f, along with its system sibling Kepler 62e, demonstrated that planets orbiting cooler stars could still be superb candidates for life, proving that habitable zones are not one size fits all, and that a world's own atmospheric chemistry can be just as important as its orbital address. Now we turn our attention to Kepler 442b, a world that, in at least one crucial way, might actually have an advantage over our own planet. Orbiting a star over 1,000 light-years away, this super-Earth receives light from its orange dwarf star that is remarkably similar in spectrum and intensity to the sunlight that bathes Earth. This is a significant factor for any potential photosynthetic organisms. In fact, some complex calculations of the Earth Similarity Index have suggested that Kepler 442b could potentially be even more hospitable for life than Earth itself. Its parent star, a K-type orange dwarf, offers a more stable and longer-lived environment than our own G-type Sun, with a lifespan measured in tens of billions of years. This provides an enormous window of opportunity for life to not only emerge but to evolve into incredibly complex forms. While it is about a third more massive than Earth, which would result in stronger surface gravity, its orbit within the heart of the habitable zone and its receiving of just enough stellar energy make it a top-tier candidate for a truly Earth-like world. From a world that might be superior to ours, we move to one of the most tantalizingly familiar discoveries from the Kepler mission. Kepler 1649c was a planet that was almost missed, hidden in the old data, and only discovered years after the telescope's primary mission ended by a team of scientists and citizen scientists painstakingly reviewing the results. This rocky, Earth-sized world orbits within the habitable zone of its red dwarf star, located 300 light-years away. What makes it so captivating is not just its size, but the amount of stellar radiation it receives. 75% of the light Earth gets from the Sun. This places it in a truly temperate range. However, this world also presents a fascinating puzzle and a note of caution. Its radius is almost identical to Earth's, but its location and the type of star it orbits have led some scientists to speculate that its environment could be more similar to Venus than to Earth, potentially blanketed by a thick, toxic atmosphere that creates a runaway greenhouse effect. It serves as a powerful reminder that being Earth-sized and in the habitable zone does not automatically mean Earth-like. It could represent either a promising abode for life or a terrifying warning of a planetary path gone wrong. Returning to our closest stellar neighbor, the Proxima Centauri system has more to offer than just the promising yet challenged Proxima Centauri b. Astronomers were surprised to discover a second world, Proxima Centauri c, orbiting much farther out in the cold depths of the system. This planet is a super-Earth or mini-Neptune, with an orbit that takes it over 5 times farther from its star than its sibling. This places it far outside the traditional habitable zone, in a region where surface water would permanently freeze. But this distance is precisely what makes it so intriguing from an astrobiological perspective. A planet this cold could potentially host a subsurface ocean on any large, icy moons it might possess, much like Saturn's Enceladus or Jupiter's Europa in our own solar system. Alternatively, if Proxima Centauri c itself has an exceptionally massive and dense hydrogen atmosphere, the internal pressure could generate enough heat to maintain a liquid water ocean deep beneath the clouds, completely isolated from the frozen surface above. While it is a much longer shot for life than its inner sibling, its existence proves that even in a single system, the possibilities for habitable environments can be astonishingly diverse. Returning to the incredible TRAPPIST-1 system, we find another world that captures the scientific imagination. TRAPPIST-1f is the 5th planet from its ultra-cool dwarf star, and like its sibling TRAPPIST-1e, it orbits within the system's habitable zone. While it receives slightly less energy from its star, placing it on the cooler outer edge of this life-friendly region, this could work in its favor. A cooler position might mean that any water present is more likely to be liquid rather than boiling away into steam. Its size is slightly larger than Earth's, but its lower density is particularly intriguing. This suggests that TRAPPIST-1f could be a world rich in volatiles, elements, and compounds that easily form gases or liquids. Scientists theorize it might possess a substantial amount of water, potentially making it a true ocean world with a global sea far deeper than any on Earth. The possibility of a liquid water ocean, combined with a rocky seafloor that could host hydrothermal vent systems, makes this planet a compelling candidate for aquatic life, existing in an eternal, star-lit aquatic realm. Shifting our gaze to a nearby stellar neighbor, we encounter GJ 273b, also known as Lytton Star b. Located a mere 12 light-years from Earth, this super-Earth orbits comfortably within the habitable zone of its quiet red dwarf star. What sets this planet apart is the remarkable stability of its parent star. Unlike the flare-prone red dwarfs that threaten many other worlds on our list, Lytton Star is exceptionally calm and old, offering a consistent and gentle flow of light and heat for billions of years. This longevity is a gift to potential life, providing the stable environmental conditions necessary for chemistry to become biology and for that biology to evolve over eons. The planet itself is a fascinating subject. With a mass about 3 times that of Earth, it likely has a robust rocky composition and strong enough gravity to hold onto a significant atmosphere. This combination of orbital position, stellar stability, and planetary characteristics makes GJ 273b one of the most promising targets for future atmospheric studies, a world that has enjoyed peace and quiet for long enough that life may have taken root and flourished. Our final stop in this group takes us to a super-Earth that offers a potential solution to one of the biggest challenges for habitability around red dwarfs. HD 40307G orbits a star 42 light-years away, but it stands out because of its relatively wide orbit. While its star is a K-type dwarf, slightly larger and brighter than a typical red dwarf, many planets orbiting such stars are tidally locked, forever presenting one face to their sun. However, HD 40307G's orbit is long enough that it might actually rotate on its axis, creating a day-night cycle much like our own. This rotation would prevent the extreme temperature differences that plague tidally locked worlds, allowing for a more even distribution of heat and the potential for stable, Earth-like climate systems. With a mass at least 7 times greater than Earth's, this planet could possess a very thick atmosphere, and its location within the outer portion of the habitable zone suggests a cooler environment that might be rich with liquid water. It represents a class of worlds that could offer the best of both worlds, the longevity of a K-dwarf star and the familiar, life-friendly dynamics of a rotating planet. Now we turn to a true pioneer in the history of exoplanet hunting, a world that captured global headlines and expanded our sense of what's possible. Kepler-22b holds the historic honor of being the very first planet discovered by the Kepler Space Telescope to orbit squarely within the habitable zone of a Sun-like star. Located 600 light-years away, this super-Earth is about twice the size of our own planet, orbiting its G-type star every 290 days. That orbital period is remarkably similar to Earth's year, and the amount of starlight it receives is about 25% less than what we get from the Sun, placing it in a comfortable position where liquid water could potentially exist on its surface. While its exact composition remains a mystery, its size suggests it could be either a massive rocky world or a mini Neptune with a deep gaseous envelope. The thrilling possibility, however, is that Kepler-22b could be a vast water world, a planet with a global ocean hundreds of miles deep covering its entire surface, a solitary and profound ocean under an alien sun. Venturing much closer to home, we find a super-Earth that is practically in our own celestial backyard. Wolf 1061c is located just 14 light-years away, making it one of the closest known potentially habitable planets to Earth. It orbits a stable red dwarf star, completing a full revolution in just 18 days. This incredibly compact orbit is typical for planets around cooler stars, as they must huddle close to their sun to stay warm. Wolf 1061c is about 4 times the mass of Earth, almost certainly locking it into a rocky composition with enough gravity to hold onto a substantial atmosphere. The central question surrounding this world is the nature of that very atmosphere. Depending on its composition, it could either be a scorching Venus-like hellscape with a runaway greenhouse effect or a more temperate world where heat is distributed effectively across its surface. Its proximity makes it an excellent candidate for future study with advanced telescopes, which could finally analyze its air and determine if this nearby neighbor is a friend or a foe in the search for life. Our journey through these diverse environments brings us to a world that experiences a reality we can barely imagine, a sky with 2 suns. Kepler-283c orbits one star in a binary system located 1,700 light-years away. This introduces a dynamic and complex environment, as the gravitational influence of a second star can potentially destabilize planetary orbits or alter climates over long timescales. Yet, despite this apparent chaos, Kepler-2 83c manages to maintain a stable path within its star's habitable zone. Its existence is a powerful testament to the resilience of planetary systems and dramatically expands the potential real estate for life in the galaxy. Scientists now believe that binary and even triple star systems, once thought to be too chaotic for stable, life-bearing planets, could in fact host numerous worlds where conditions are just right. If this planet possesses a sufficiently strong magnetic field and a robust atmosphere, it could well be shielded from the gravitational stresses of its twin suns, creating a sheltered pocket where life could take hold and gaze up at a double sunrise. Our exploration now brings us to a super-Earth that demonstrates how planetary mass can dramatically reshape a world's potential. Just 16 light-years away, GJ832c is a heavyweight contender, a planet with a mass at least 5 times greater than Earth's. This formidable bulk places it right on the boundary between a rocky super-Earth and a gaseous mini-Neptune, creating a fascinating astrobiological puzzle. Its orbit is unusually elongated, which would send it swinging between the cooler outer edges and warmer inner regions of its star's habitable zone. This eccentric journey could theoretically create wild seasonal shifts in climate. However, its most defining feature is likely the tremendous gravity generated by its immense mass. This powerful force would be more than capable of holding onto an incredibly dense and extensive atmosphere, perhaps dozens of times thicker than our own. Such an atmosphere could act as a global pressure cooker, efficiently distributing heat and potentially creating a stable, warm environment across the entire planet, possibly even with a global ocean beneath the clouds. The central question is whether this thick shroud is primarily hydrogen and helium, like a gas giant, or a more substantial mix of nitrogen, carbon dioxide, and water vapor, which would be far more promising for life as we know it. In stark contrast, we encounter a world that serves as a sobering lesson in the fragility of habitability. Kepler-438b, located over 600 light-years away, once ranked among the most Earth-like planets ever discovered based on its size and the amount of light it receives from its K-dwarf star. Its physical characteristics are strikingly familiar, earning it an extremely high Earth Similarity Index score and sparking initial excitement about its potential. Yet, this promise is tragically undermined by the very nature of its parent star. Kepler-438 is a profoundly volatile star, prone to erupting in superflares, cataclysmic outbursts of radiation that are orders of magnitude more powerful than anything our Sun has ever produced. These flares are so intense and frequent that astronomers believe they have likely stripped away any atmosphere the planet may have once possessed, bombarding its barren rock surface with lethal levels of ultraviolet and X-ray radiation. Kepler-438b stands as a poignant reminder that a planet's location and size are only part of the equation. A calm and stable parent star is an equally critical ingredient for nurturing and sustaining a living world over billions of years. Completing this trio is a planet that offers a more optimistic outlook from within a complex multi-planet system. Kepler-296e is part of a fascinating family of 5 known worlds, all orbiting a star system nearly 1,200 light-years from Earth. This planet is particularly special because it orbits squarely within the habitable zone of its 2 red dwarf stars, which themselves orbit each other. Kepler-296e's size, only about 1.5 times that of Earth, makes a rocky composition highly probable, and its position suggests surface temperatures that could be ideal for large bodies of liquid water to exist. Being part of a packed system introduces intriguing possibilities. If any of its sibling planets are gas giants with large moons, those moons could also be habitable, creating multiple chances for life within a single celestial neighborhood. While the dynamics of a binary star system add complexity, The potential for a temperate, rocky world like Kepler-296e demonstrates that even in more crowded and dynamic stellar environments, nature can still carve out stable, life-friendly orbits. Leaving behind the volatile flares of Kepler-438, we arrive at a world where time itself moves at a different, more deliberate pace. Kepler-440b is a super-Earth that takes a stately 101 days to complete a single orbit around its K-type star. This longer orbital period, compared to the frantic few weeks common for planets around cooler stars, suggests it lies a bit farther out, a positioning that could be its greatest strength. The increased distance from its sun might allow Kepler-440b to avoid the fate of tidal locking, potentially granting it a rotating day-night cycle much like our own. This rotation would prevent the brutal extremes of permanent day and eternal night, instead distributing stellar energy more evenly across the planet and fostering a far more stable and temperate global climate. This stability, combined with its location in the habitable zone, paints a picture of a world that could have enjoyed billions of years of consistent, life-friendly conditions. Our next destination presents one of the most promising statistical profiles for life we have ever encountered. Kepler-1229b is an exoplanet that consistently ranks among the very top of all known worlds on the Earth Similarity Index. Located over 700 light-years away, it orbits squarely within the habitable zone of its red dwarf star. Its radius is almost identical to Earth's, strongly suggesting a rocky composition with a solid surface of continents and ocean basins. The amount of sunlight it receives is strikingly similar to our own planet's, meaning its potential surface temperature could be remarkably Earth-like. This combination of familiar size, familiar energy input, and a prime orbital location makes it a premier candidate for a truly Earth analog world. The possibility of liquid water on its surface seems exceptionally high, and its parent star, while a red dwarf, appears to be less volatile than many of its stellar cousins, offering a more stable platform for the delicate chemistry of life to begin and persist across the eons. Rounding out this trio is a world whose discovery highlights the incredible precision and legacy of the Kepler mission. Kepler-1544b is another rocky super-Earth discovered by the Kepler telescope as it monitored the subtle dimming of starlight caused by a planet transiting across the face of its sun. This planet, orbiting a quiet and stable K-dwarf star, is positioned perfectly within the star's habitable zone. The nature of its star is particularly significant. K-dwarfs are often considered Goldilocks stars in the search for life. They are more stable and longer-lived than restless red dwarfs, yet far more common than stars like our own sun. This offers a tranquil environment with a lifespan of tens of billions of years, an almost unimaginable amount of time for biological evolution to work its magic. While we await more data on its atmosphere, the fundamental ingredients are all there. A rocky world, the right amount of stellar energy, and a calm, ancient star providing a steady, unwavering light. It represents the quiet, promising hope of a world that has had all the time in the universe to become inhabited. Turning our attention to the final three worlds on our list, we begin with Kepler-705b, a super-Earth that exemplifies how resilience might be the key to survival in a challenging environment. Orbiting a cool K-type star over 1,000 light-years away, this planet is significantly more massive than Earth, a characteristic that could be its greatest asset. While its orbit places it on the cooler outskirts of the habitable zone, its substantial size opens up two fascinating possibilities for harboring life. The first is a thick, insulating atmosphere rich in greenhouse gases like carbon dioxide or methane. Such a dense atmospheric blanket could effectively trap the limited stellar heat, transforming what might otherwise be a frozen wasteland into a temperate world capable of supporting liquid water on its surface. The second, even more intriguing possibility is a subsurface ocean. The planet's strong gravity could maintain geological activity, generating internal heat from a radioactive core. This heat, locked deep beneath a frozen icy crust, could power a vast, hidden ocean similar to the one on Jupiter's moon Europa. In this scenario, life wouldn't bask in the light of its sun, but would thrive in the eternal darkness of a deep, warm, subterranean sea, completely isolated from the conditions on the surface above. Next, we encounter a world that feels like a classic textbook candidate for an Earth twin. Kepler 1090b orbits a star very similar to our own Sun, and its fundamental statistics are incredibly promising. Its size is almost identical to Earth's, strongly suggesting a rocky composition with familiar geography of mountains, valleys, and potentially vast ocean basins. Its orbital period of just over 200 days places it comfortably within its star's habitable zone, receiving a stellar flux that should, in theory, allow for liquid water to pool on its surface. However, this world, located approximately 2,000 light-years away, presents the immense challenge of conformation that plagues so many distant exoplanet discoveries. The extreme distance and the relative faintness of its star make it extraordinarily difficult for our current telescopes to analyze its atmosphere for the telltale biosignatures of life, such as oxygen or methane. Kepler 1090b represents the tantalizing future of exoplanet science. It is a prime target waiting for the next generation of space-based observatories, a world whose true nature and potential will remain a beautiful mystery until our technology finally catches up to our ambition and allows us to peer into its air for the first time. Concluding our journey through 30 remarkable worlds is Kepler 1606b, a discovery that perfectly encapsulates the diversity and sheer wonder of this ongoing search. This super-Earth, found by the tireless Kepler telescope, orbits within the habitable zone of its star, but its true significance lies beyond its individual characteristics. Its inclusion on this list highlights a profound truth we've learned from thousands of exoplanet discoveries. The galaxy is overflowing with an astonishing variety of planets. We've found worlds that are water-rich hycean planets shrouded in hydrogen, tidally locked planets with eternal twilight zones, and rotating planets with familiar day-night cycles. We've discovered planets in triple star systems and planets orbiting calm, ancient stars that have been stable for longer than our Sun has existed. Kepler 1606b is a part of that incredible tapestry. It may not be the most Earth-like or the closest, but it stands as a testament to the fact that habitable environments are not confined to a single, narrow template. The conditions that could give rise to life are as diverse and creative as the universe itself, and each new world we find expands our understanding of where and how life might just find a way. But what exactly makes a planet just right? For decades, scientists have used the concept of the habitable zone, often poetically called the Goldilocks Zone, to guide this cosmic search. It's the orbital region around a star where conditions are neither too hot nor too cold, but just right for liquid water to potentially exist on a planet's surface. This isn't a guarantee of life, but rather the finding of a promising address in the galaxy where the most crucial ingredient for life as we know it could be stable. However, the size and location of this zone are not fixed. They are dramatically sculpted by a complex interplay of three key factors: the star's temperament, the planet's physical character, and the nature of its atmospheric blanket. The star is the master architect, dictating the very boundaries of possibility. Consider our own Sun, a stable G-type star. Its habitable zone is a relatively wide band, with Earth orbiting comfortably in the middle. But for the most common stars in our galaxy, the red dwarfs like Proxima Centauri or TRAPPIST-1, the story is completely different. These stars are far cooler and dimmer, which means their habitable zones are incredibly close in and narrow. A planet must huddle very near its star to receive enough warmth, often resulting in tidal locking. Yet these stars offer a tantalizing trade-off: astonishing longevity. While a sun-like star shines for about 10 billion years, a red dwarf can burn steadily for trillions of years, offering an unimaginably long window for life to arise and evolve. On the other end of the spectrum, larger, hotter stars have much wider habitable zones, but their brilliant, furious lives are cut short in just a few million years, likely snuffing out any chance for complex life to develop before the star itself dies. A planet's own physique is the second critical piece of this puzzle. Its mass and composition determine whether it can even hold onto the environments that life needs. A world too small, like Mars, will lack the gravity to maintain a substantial atmosphere, allowing liquid water to boil away into space and leaving the surface barren and exposed. A world too large, perhaps 10 times Earth's mass, might gravitationally accrete a massive, crushing envelope of hydrogen and helium gas, becoming a mini Neptune without a solid surface at all. The sweet spot appears to be a rocky planet with enough mass somewhere between half and twice Earth's size to generate a protective magnetic field and sufficient gravity to retain a life-sustaining atmosphere for billions of years. This is why the discovery of Earth-sized planets like Kepler 1229b was so revolutionary. They hit this planetary bullseye. Ultimately, a planet's atmosphere acts as its global thermostat and shield, and it can completely redefine the Goldilocks zone. We see this on a small scale in our own solar system. Venus, Earth, and Mars all orbit within the Sun's broad habitable zone, yet only Earth is habitable. Venus succumbed to a runaway greenhouse effect, its thick atmosphere turning it into a scorching hellscape, while Mars's thin air couldn't hold onto its heat and water, leaving it a frozen desert. This principle applies dramatically to exoplanets. A planet like LHS 1114b, which receives less stellar energy than Earth, could use a dense greenhouse gas-rich atmosphere to trap heat and maintain balmy temperatures. Conversely, a thick atmosphere on a world like GJ 357d could prevent its limited heat from escaping, transforming a frigid orbit into a temperate one. This means the traditional concept of a habitable zone is constantly evolving. A planet doesn't need to be in the perfect spot. It just needs the right atmospheric chemistry to create its own perfect conditions, turning what might seem like a frozen wasteland into a potential ocean world. So, how do we actually search for life on these distant worlds when they are so far beyond our reach? The answer lies not on their surfaces, but in the very air that might surround them. We hunt for atmospheres, and within those veils of gas, we search for the faint chemical whispers of biology, what scientists call biosignatures. An atmosphere is far more than just a layer of air. It is a planet's breath, a dynamic and complex mixture of gases that can tell a profound story about what is happening on the ground below. It can reveal a world's history, its climate, and most excitingly, whether it might be a living world. Think of a planet's atmosphere as a chemical fingerprint. On Earth, our atmosphere is wildly out of balance. It contains large amounts of oxygen, a highly reactive gas that readily combines with other elements like iron, which is why metal rusts. Without a constant, massive source replenishing it, all the oxygen in our air would vanish in just a few million years. That massive source is life itself, photosynthetic organisms like plants and algae that continuously pump oxygen into the atmosphere as a waste product. Similarly, methane is another gas that is quickly broken down by sunlight. Its persistent presence in our air is also largely due to biological sources, from bacteria to livestock. So, when astronomers look at an exoplanet, they aren't just looking for any atmosphere. They are looking for an atmosphere that is chemically unstable, one that contains gases which shouldn't coexist for long without something, perhaps life, actively maintaining them. A simultaneous detection of both oxygen and methane, for example, would be a tremendously exciting, though not definitive, sign. The primary method for this delicate detective work is called transmission spectroscopy. When a planet transits or passes in front of its host star from our point of view, A tiny fraction of the star's light filters through the planet's atmosphere on its way to us. Different gases in that atmosphere absorb specific wavelengths of this light, leaving behind dark lines in the star's spectrum, a unique barcode that reveals the atmosphere's chemical composition. This is how the landmark discovery on K218b was made, by meticulously analyzing the light that passed through its hycean world atmosphere. Scientists detected the unmistakable signature of water vapor. This was a historic moment, the first time we had ever identified water in the atmosphere of a planet residing in its star's habitable zone. It didn't confirm life, but it confirmed the presence of the single most important ingredient for life as we know it, on a world with a completely new and alien environment. However, this search is incredibly difficult and requires interpreting clues with extreme caution. A biosignature is not a confirmed discovery of life. It is a sign of something that could be life, but might also be explained by unusual geological or chemical processes. For instance, oxygen can be produced abiotically through the breakdown of water vapor by intense ultraviolet radiation. Methane can be vented by volcanic activity. This is why the most promising biosignature is not a single gas, but a suite of them, a combination of oxygen, methane, and perhaps other gases like nitrous oxide, all out of equilibrium and with no plausible non-biological explanation for their abundance. Furthermore, scientists are also beginning to search for technosignatures, signs of advanced technology, such as artificial light on the night side of a tidally locked planet or industrial pollutants in an atmosphere that could indicate not just life but intelligent civilization. This is where the future of the search truly comes into focus, led by a new generation of extraordinary telescopes. NASA's James Webb Space Telescope is already revolutionizing this field. With its massive gold-coated mirror and incredibly sensitive infrared instruments, it is capable of performing detailed atmospheric spectroscopy on nearby rocky exoplanets for the very first time. Its targets include some of the most promising worlds on our list, like the TRAPPIST-1 planets. Imagine Webb staring at TRAPPIST-1e as it transits, patiently collecting the faint starlight that has filtered through its air, searching for those telltale absorption lines that could indicate oxygen, water, or methane. Similarly, plans are underway for even more powerful future observatories, like the Habitable Worlds Observatory, a space telescope concept designed with the primary goal of directly imaging Earth-like planets and analyzing their atmospheres to search for evidence of life. The search for biosignatures is a painstaking process of elimination, a cosmic balancing act of hope and rigorous skepticism. Each new atmospheric spectrum is a piece of a grander puzzle. A detection of water vapor, like on K218b, is a thrilling first step. A potential future detection of oxygen and methane on a world like Proxima Centauri b would be a monumental second step. But the final confirmation will likely require multiple lines of evidence from different telescopes, ruling out all non-biological explanations until only one extraordinary conclusion remains. We are on the precipice of this new era, building the tools that may, within our lifetimes, finally answer the question of whether the chemical fingerprints we find in the skies of distant worlds are indeed the signatures of another living planet. While a planet's location and atmosphere are crucial, the star it orbits plays an equally vital and often volatile role as the ultimate arbiter of life. Stellar activity, the temperament and behavior of a star, can either nurture a world for billions of years or ruthlessly sterilize it in a cosmic instant. This dramatic interplay between star and planet creates a fundamental divide in the potential for life, separating the truly promising worlds from those that are merely tantalizing mirages. Consider the most common stars in our galaxy, red dwarfs. Many of these diminutive suns are prone to violent and frequent tantrums in the form of powerful stellar flares. These aren't like the solar flares from our own relatively placid sun. A red dwarf flare can erupt with the energy of thousands of solar flares at once, unleashing a torrent of X-rays and ultraviolet radiation that bathes any nearby planet. This is the grim reality for a world like Kepler 438b. Despite its perfect Earth-like size and ideal location in the habitable zone, its parent star's ferocious superflares are believed to have relentlessly scoured the planet, likely stripping away its entire atmosphere and bombarding its surface with enough radiation to shatter any complex molecules. For planets orbiting such hostile stars, the habitable zone is a cruel misnomer. It may be a region where liquid water is thermally possible, but it is certainly not a region where life could ever survive the onslaught. Yet, not all red dwarfs are created equal, and this is where the search becomes more nuanced and hopeful. Stars like Ross 128 offer a completely different, more serene environment. This ancient red dwarf is remarkably inactive, a calm and stable beacon that has likely provided a gentle, consistent flow of light and heat for billions of years. For a planet like Ross 128b, this stellar tranquility is its greatest blessing. Shielded from the atmospheric eroding effects of constant flares, such a world would have a much higher chance of holding onto its life-sustaining atmosphere and allowing the delicate chemical reactions of biology to begin and flourish. The longevity of these quiet stars is their other great gift. Their potential trillion-year lifespans provide an almost unimaginable window for life to not only emerge but to evolve into stunning complexity. A planet is not entirely helpless against its star's wrath, however. Its own internal characteristics can provide a powerful defense. This is where a strong global magnetic field becomes a critical shield for habitability. Generated by the churning of a molten metal core, a magnetic field acts as an invisible force field, deflecting and channeling a star's most damaging charged particles away from the atmosphere and toward the poles where they might create brilliant auroras rather than cause destruction. A world like LHS 1140b, a massive super-Earth, is a prime candidate for possessing such a protective magnetosphere. Its considerable size suggests it has retained enough internal heat to power a dynamic core for billions of years, generating a magnetic field potentially far stronger than Earth. This powerful shield could be the very reason it might still possess the thick, insulating atmosphere that theorists believe keeps it warm, effectively holding its ground against the stellar wind and preserving the conditions necessary for its potential global ocean. In the cosmic battle between star and planet, a magnetic field is a world's best armor. This dramatic phenomenon, known as tidal locking, presents one of the most fascinating and challenging environments for potential life in the universe. It occurs when the gravitational pull between a planet and its star becomes so strong that it synchronizes the planet's rotation with its orbit. The result is a world forever fixed in place, with one hemisphere perpetually bathed in blistering sunlight and the other plunged into the deep freeze of eternal night. For a planet like Proxima Centauri b, which must huddle extremely close to its faint red dwarf star to stay warm, this is not a possibility but a near certainty. The stark temperature difference between these two sides would be immense, creating a searing hot pole and a frigid cold pole, with a gradient of environments in between. Yet, this doesn't automatically render such a world sterile. The most promising region for life would likely be the thin ribbon of twilight that circles the planet, known as the Terminator line. Here, the sun would forever hover on the horizon, offering a perpetual, gentle sunrise or sunset. This twilight zone could enjoy moderate temperatures, a stable climate, and the potential for liquid water, a true oasis between two extreme wastelands. Life here would be utterly unique, perhaps with vegetation that grows laterally to forever chase the low-hanging sun, or organisms that have evolved to make the most of the constant, dim light. Furthermore, a substantial atmosphere could completely reshape this harsh reality. Powerful atmospheric circulation patterns would act as a planetary heating and cooling system, with winds relentlessly transporting heat from the scorching day side to the frigid night side. This could dramatically moderate the extreme temperatures, potentially creating a band of habitability that wraps around the entire planet, making even the surface of the night side warmer than it would otherwise be. The contrast with a rotating world like Kepler 186f could not be more profound. While we don't know its rotational status for certain, the possibility that it spins offers a much more familiar and perhaps more forgiving template for life. A day-night cycle means solar energy is distributed evenly across the globe, preventing any single region from becoming lethally hot or cold. This rotation fosters predictable weather patterns, stable seasons, and a more uniform environment where life could emerge and diversify across the entire planet, rather than being confined to a narrow strip of land. It allows for the evolution of creatures adapted to the full spectrum of environments, from the equator to the poles, from deep oceans to high mountains. The existence of such rotating planets expands our view of cosmic habitability, suggesting that while tidally locked worlds present incredible challenges that life might still overcome, worlds with a daily cycle offer a broader, more stable canvas for biology to paint its masterpiece. This distinction between super-Earths and mini-Neptunes is one of the most critical frontiers in the search for life, a fundamental divide that separates solid, potentially familiar worlds from those that are utterly alien yet perhaps just as habitable. On one side, we have super-Earths, planets like GJ 357d, which are fundamentally rocky worlds just like our own, but scaled up to several times Earth's mass. Their greater bulk suggests a stronger gravitational pull, meaning if you were to stand on the surface of GJ 357d, you would feel significantly heavier, perhaps even 2 or 3 times your Earth weight. This powerful gravity is a double-edged sword. It's excellent for holding onto a life-sustaining atmosphere, preventing it from being stripped away by stellar winds, but it also creates immense pressure that would make any geological activity or tectonic movement far more intense and potentially volatile. The very landscape itself would be shaped by these forces, with mountains likely being lower and broader due to the crushing weight they must support, and any potential life forms would need to be incredibly robust, adapted to a world of heavy gravity and potentially a very dense, thick atmosphere. On the other side of this planetary divide are the mini-Neptunes, a class of world for which we have no direct analog in our own solar system. These are not simply larger versions of Earth, they are fundamentally different, smaller cousins of the gas giants Uranus and Neptune. A hycean world like K218b is the perfect example of a mini-Neptune. It possesses a relatively small rocky core, but that core is utterly engulfed by a deep, massive envelope of hydrogen and helium gas, an atmosphere that could be hundreds of miles thick, creating surface pressures thousands of times greater than what we experience on Earth. There is no solid surface to stand on. Instead, the atmosphere would just get progressively denser and hotter as you descend, eventually turning into a supercritical fluid, a strange, high-pressure state where the distinction between liquid and gas blurs into oblivion. The surface conditions, if we can even call it that, would be utterly crushing and incompatible with any life as we know it. Yet, the incredible revelation about these hycean mini-Neptunes is that life might not need a surface at all. The true potential for habitability on a world like K218b lies not at the bottom of its atmosphere, but at a specific Goldilocks layer within it. Deep beneath the crushing upper clouds, where the atmospheric pressure becomes immense but the temperature stabilizes to a range similar to Earth's oceans, there could exist a global liquid water ocean. This is not an ocean resting on rock, but a vast sea suspended within the planet's own atmosphere, a profound and alien abyss. In this eternal, dark ocean, shielded from the hostile space above by a blanket of hydrogen, the chemical ingredients for life could mix and interact, potentially giving rise to microbes or other organisms that thrive in the complete absence of sunlight, much like the ecosystems around hydrothermal vents in Earth's deepest seas. The search for life, therefore, expands from just looking for Earth twins to considering these bizarre, ocean-bearing mini-Neptunes, reminding us that nature's creativity in crafting habitable environments far exceeds our own imagination. Imagine a world without continents, without mountains breaking a global horizon, a planet where the only view in every direction is an endless, gentle swell of water under a hazy sky. This is the captivating possibility of an ocean planet, a world completely enveloped by a single, planet-wide sea hundreds of miles deep. Worlds like TOI 700d and Kepler 62f present this breathtaking scenario where the very concept of land is foreign and the entire surface is a vast aquatic realm. Such an environment wouldn't simply have life in its oceans. The entire planet would be an ocean, a global ecosystem of staggering scale and depth. The conditions there would be profoundly alien, with immense pressures at the abyssal depths and a water cycle utterly dominated by evaporation and precipitation over a boundless expanse. Yet within this eternal sea, the potential for life is not just possible, it might be thriving in ways that challenge our terrestrial biased imagination. Aquatic life on such a water world could evolve into forms and complexities we can scarcely conceive. In the sunlit upper layers, vast floating mats of alien algae might form the base of a food web, supporting schools of bizarre filter feeders that drift on perpetual currents. Descending into the twilight zones, life might generate its own light through bioluminescence, creating dazzling displays in the perpetual darkness to attract prey or mates. The real cradle of life, however, might lie at the very bottom, in the crushing depths where no sunlight ever penetrates. Here, the planet's internal heat could fuel a network of hydrothermal vents, spewing mineral-rich, superheated water into the icy blackness. On Earth, such vents are oases of life, hosting entire ecosystems of tube worms, blind shrimp, and unique bacteria that derive their energy not from the sun, but from chemosynthesis processing chemicals like hydrogen sulfide. On an ocean world, these vent systems could be far more extensive and stable, having operated for billions of years, potentially giving rise to intelligent, deep-sea civilizations that have never seen the stars or even known that a surface exists. For astronomers trying to detect life from across the light years, a water world presents a unique and formidable challenge. Our primary strategy involves analyzing the atmospheres of these planets for biosignatures, the chemical byproducts of life. But on a world with no land, some of the most recognizable signs might be absent or different. For instance, the oxygen in Earth's atmosphere is largely produced by photosynthetic life on land and in shallow seas. On a planet with no continents, the balance of atmospheric gases could be radically altered. The primary biological activity might produce different signatures, like abundant dimethyl sulfide or other gases less common on Earth. Furthermore, a thick layer of water vapor in the atmosphere, constantly evaporating from the global ocean, could make spectral analysis more difficult, obscuring the fainter signals of biological gases. We might need to look for subtler clues, like an atmosphere that is persistently out of chemical equilibrium, in a way that only a continuous planet-wide biosphere could maintain. The role of hydrothermal vents cannot be overstated. They may be the universal spark for life on water worlds. These geological features, where a planet's internal heat meets its ocean, provide not just energy but also a rich soup of chemicals and mineral substrates that are ideal for the complex chemistry that leads to life. The stability of these environments is key. While surface conditions can be ravaged by asteroid impacts, solar flares, or climatic shifts, the deep-sea vent systems on an ocean planet are incredibly insulated, potentially offering a safe haven for life to originate and persist for eons undisturbed. If life begins in these deep, dark cradles, it might never have a reason to leave, evolving into entirely subsurface ecosystems that we could only hope to detect through the faintest traces of metabolic waste products that slowly diffuse up to the ocean surface and into the atmosphere. The search for life on these enchanting water worlds forces us to broaden our definition of habitability and consider that the most common abode for life in the cosmos might not be a twin of Earth, but a planet with no land at all, a solitary jewel of blue hanging in the blackness of space. Now, let's venture into one of the most dynamic and visually spectacular environments imaginable: planetary systems with not one, but multiple suns. For a long time, scientists believed that binary or even triple star systems would be far too chaotic and gravitationally unstable to host planets capable of supporting life. The constant gravitational tug-of-war between multiple stars, it was thought, would either fling planets into the depths of space or send them on wildly erratic orbits, creating temperature swings so extreme that no liquid water could persist. But the discovery of worlds like GJ 667cc has completely upended that assumption, proving that nature is far more creative and resilient than we ever imagined. These multi-sun systems aren't just celestial curiosities. They are legitimate and perhaps even common harbors for habitable worlds, presenting a set of challenges and opportunities for life that are utterly alien to our single-sun experience. To understand how a planet can survive and even thrive in such a complex environment, we need to look at the architecture of its stellar neighborhood. GJ 667cc is a perfect case study. It doesn't orbit all three stars in its system simultaneously. Instead, it has a very close, tight orbit around the smallest star of the trio, a red dwarf designated GJ 667c. The two other, more massive stars orbit each other at a much greater distance, and this entire binary pair then orbits the red dwarf and its planet from even farther away. This hierarchical structure is the key to stability. From the perspective of the planet, it has one clear primary sun. The two other stars are so distant that they would appear simply as exceptionally bright points of light in the sky, perhaps casting a faint secondary glow but contributing very little actual heat. This arrangement effectively shields the planet from the gravitational chaos that would exist if all the stars were closer together, providing it with a stable, predictable orbit and a consistent source of warmth from its parent red dwarf. This doesn't mean the sky would be anything less than breathtaking. Imagine a sunrise where one brilliant sun crests the horizon, followed sometime later by a second, much smaller but still intensely bright star, and then as darkness falls, a third sun-like point of light becomes the brightest object in the twilight sky. The cycles of light and dark would be complex, with periods of single daylight, double daylight, and extended twilight, creating a daily rhythm completely foreign to our 24-hour cycle. For life on the surface, this could actually be an advantage. The varying angles and intensities of light could drive incredibly diverse evolutionary adaptations in photosynthetic organisms, for instance, or create microclimates that are more temperate than a single star system might allow. The true test of habitability in these systems lies in the orbital dynamics. For a planet to avoid those fatal temperature swings, its path around its host star must be nearly circular. An elliptical or oval-shaped orbit would send the planet swinging dramatically closer to and farther from its star, leading to extreme seasonal changes that could boil oceans and then freeze them solid. The remarkable thing about planets like GJ 667cc is that their orbits within these complex multi-star systems can indeed be very stable and circular. This is often because the planet's orbit is so tightly bound to its primary star that the gravitational influence of the other, more distant stars is too weak to significantly perturb it. It's like a child holding their parent's hand tightly in a busy crowd. The surrounding noise and movement are there, but the primary connection provides safety and stability. Could life actually thrive under such dynamic skies? The answer seems to be a cautious yes, provided the planet has another crucial feature, a robust atmosphere. A thick atmospheric blanket would act as a buffer against any minor variations in stellar radiation. using its insulating properties to distribute heat evenly across the planet and maintain a relatively stable global temperature. This atmospheric buffer could smooth out the edges of even a slightly eccentric orbit or the subtle changes in light from multiple suns, creating a climate that is far more forgiving than the raw orbital mechanics might suggest. The existence of these worlds forces us to expand our definition of a habitable environment, proving that life's potential is not confined to the calm, solitary suns, but might also flower under the watchful gaze of multiple dancing stars in the sky. The hunt for definitive answers about these 30 worlds is accelerating, driven by a new generation of technological marvels that will push the boundaries of what we can see and know. Leading this charge is the James Webb Space Telescope, an instrument that is already revolutionizing our view. Webb's immense power lies in its ability to perform incredibly detailed atmospheric spectroscopy, analyzing the faint starlight that filters through an exoplanet's air during a transit. For nearby rocky planets like those in the TRAPPIST-1 system, Webb can search for the chemical fingerprints of water vapor, methane, carbon dioxide, and even oxygen, providing our first real clues about the conditions on their surfaces. It's our first real chance to move from simply detecting these planets to truly characterizing them, transforming them from distant points of light into real worlds with weather, chemistry, and perhaps even signs of a biosphere. But the quest doesn't end with Webb. On the horizon are even more ambitious missions, each designed to answer a specific piece of this cosmic puzzle. The PLATO mission, led by the European Space Agency, is a planet hunter extraordinaire. Its primary goal is to find and confirm Earth-sized planets orbiting Sun-like stars within their habitable zones, a search that will dramatically expand our catalogue of prime targets beyond the current list of 30. PLATO keen eyes will give us thousands of new candidates, but knowing a planet's size and orbit is only the beginning. To understand its true nature, we need to see it directly. This is the monumental challenge that the next wave of ground-based telescopes will tackle. Behemoths like the extremely large telescope in Chile, with a primary mirror nearly the size of a baseball diamond, will employ revolutionary direct imaging techniques. Using advanced coronagraphs that block the blinding glare of the host star, these telescopes will attempt to capture the actual, faint light reflecting off an exoplanet itself. This would be a historic achievement, allowing us to see an alien world as a distinct point of light and analyze its spectrum without waiting for a transit. Direct imaging could reveal the color of its oceans, the composition of its clouds, and even the seasonal changes on its surface, providing a holistic picture of its environment that transit spectroscopy alone cannot. The ultimate goal of all this technological marvel is the search for biosignatures, those elusive chemical signs of life. Future observatories, like the proposed Habitable Worlds Observatory, will be designed with this single purpose in mind. They will combine the light-gathering power of a massive space telescope with the stability to stare at a single star system for weeks or even months, building up an exquisitely detailed spectrum of a planet's atmosphere. They won't just be looking for a single gas like oxygen. They'll be searching for a suite of gases that are persistently out of equilibrium, a combination that can't be easily explained by geology or chemistry alone. The simultaneous presence of oxygen and methane, for example, would be a powerful indicator, as these gases rapidly destroy each other and must be continuously replenished, potentially by living processes. This isn't a distant dream, it's the roadmap for the next 2 decades. We are on the cusp of a golden age of discovery, where the names of these 30 planets will transition from scientific curiosities into fully realized worlds. The data flowing from Webb today is laying the groundwork. PLATO will give us the targets for the 2030s, and the giant ground and space telescopes of the 2040s will bring them into stunning focus. The question is no longer if we will find a planet with the right conditions for life, but when we will finally point our instruments at one and see the atmospheric evidence that we are not alone in the universe. But with such an abundance of promising real estate, from the tranquil shores of Ross 128b to the global ocean of K218b, a profound and unsettling question arises. Where is everybody? This is the core of the Fermi Paradox, the glaring contradiction between the high probability of alien civilizations and our complete lack of evidence for them. We've journeyed through 30 worlds that each present a compelling case for potential habitability, and statistically, there should be millions more like them in our galaxy alone. The universe is ancient, vast, and seemingly well-stocked with the ingredients for life, so the silence is deafening. This paradox forces us to confront a number of sobering theories, each offering a different explanation for the great cosmic quiet. One of the most discussed and disquieting ideas is the concept of the Great Filter. This theory suggests that there is at least one nearly insurmountable barrier that prevents life from progressing to the stage of a spacefaring, galaxy-colonizing civilization. The filter could lie in our past, perhaps the initial abiogenesis, the jump from non-living chemistry to a self-replicating organism, is astronomically rare. Maybe the evolution of complex eukaryotic cells, which took over 1 billion years on Earth, is the true bottleneck. If this is the case, then the filter is behind us, and we are among the first or only ones to have made it through. The alternative is far more grim. The Great Filter might still lie ahead of us. It could be that the development of advanced technology inevitably leads to self-destruction through nuclear war, climate catastrophe, or a malicious artificial intelligence. Or perhaps every civilization eventually discovers a devastating particle physics experiment or a source of energy that accidentally annihilates them. If this is true, then the eerie silence we observe is a grave warning, and the ruins of countless other civilizations that failed the test are scattered across those 30 worlds we find so promising. A less ominous but equally mind-bending explanation is the zoo hypothesis. This idea proposes that advanced extraterrestrial civilizations are indeed out there and are fully aware of us, but they have deliberately chosen to conceal their presence. They might be observing us from a distance, much like we observe animals in a wildlife preserve, adhering to a strict policy of non-interference until we reach a certain level of technological or ethical maturity. This would explain why our radio telescopes haven't picked up any clear signals. They know we're listening and are intentionally maintaining radio silence in our direction. The zoo hypothesis suggests a universe that is not empty, but rather curated, with humanity living in a designated planetary sanctuary, isolated from a much larger interstellar community until we are deemed ready to join it. Then there are the more practical, technological barriers. The distances between stars are almost incomprehensibly vast. Even Proxima Centauri b, our closest neighbor, is over 4 light-years away. A journey there with our current technology would take tens of thousands of years. An advanced civilization might eventually solve this through generation ships or hibernation technology, but the energy and resources required to travel between stars on a regular basis are staggering. It's possible that the sheer physics of interstellar travel acts as a permanent cage, keeping even the most advanced species confined to their home solar systems. Furthermore, our methods of detection might be hopelessly primitive. They could be communicating using technologies we haven't even dreamed of yet, like neutrino beams or quantum entanglement, making their signals completely invisible to our current arrays of radio dishes. We might be like islanders trying to spot passing ships by looking for smoke signals, utterly unaware of the radio transmissions crackling all around us. Perhaps the most profound answer is also the simplest: time. The universe is 13.8 billion years old, and our technological civilization is less than a few hundred years old, a mere blink of an eye on a cosmic timescale. It is entirely possible that galactic civilizations rise and fall on timescales of millions of years, meaning they are separated from each other not by space but by time. A vibrant, communicative empire could have flourished and gone extinct hundreds of millions of years ago, and another might not arise for another 100 million years. We could be looking out at a cosmic graveyard, or we could be the first faint stirrings of intelligence in a galaxy that is still waking up. The 30 planets on our list are not just places, they are moments frozen in time. We see them as they were years, centuries, or millennia ago when their light began the journey to our telescopes. We have no way of knowing what is happening there right now. The civilization whose signals we are desperately hoping to receive might have already vanished, or it might not even have emerged yet. Our search is not just a scan across space, but a reach across the deep, silent ocean of cosmic time. To truly grasp the potential for life on these alien worlds, we must first abandon our Earth-centric view of biology and expand our imagination to embrace the bizarre. Life on our own planet has proven to be tenacious, thriving in environments we once believed to be utterly inhospitable. These organisms, known as extremophiles, provide our best blueprint for what might be waiting for us in the cosmos. Consider the tardigrade or water bear, a microscopic creature that can survive the vacuum of space, intense radiation, and temperatures near absolute zero by entering a state of suspended animation. Or the chemosynthetic bacteria living around hydrothermal vents on the ocean floor, thriving in complete darkness under crushing pressures, deriving their energy not from the sun but from the chemical energy of minerals spewed from Earth's core. These are not oddities, they are proof of concept that life is not a delicate flame but a stubborn spark, capable of igniting in the most unexpected places. This understanding completely reframes the challenges posed by many of the planets on our list. A world like Proxima Centauri b, bombarded by intense stellar radiation, might not be a sterile wasteland. Instead, it could host ecosystems of organisms with incredibly efficient DNA repair mechanisms, or life forms that live deep within subsurface rocks or caverns, shielded from the radiation above. Their biology might rely on pigments or minerals that act as natural radiation shielding, turning a lethal environment into a manageable one. Similarly, the eternal darkness and crushing pressures of a hycean world's deep ocean, like on K218b, are not a barrier to life but simply the parameters for it. Entire complex ecosystems could flourish there based on chemosynthesis, with creatures perhaps possessing bioluminescence for communication and predation in the perpetual night, a dazzling underwater light show in an alien abyss. Perhaps the most exciting possibility is that life out there might not even be based on the same biochemical blueprint as life on Earth. We are carbon-based life, and for good reason. Carbon is a wonderfully versatile atom, excellent at forming the long, complex chains necessary for proteins and DNA. But what if another element could serve a similar function? Silicon is often proposed as an alternative. It sits directly below carbon on the periodic table, meaning it shares some similar chemical properties and can also form 4 bonds. A silicon-based life form could, in theory, exist. Instead of breathing oxygen and exhaling carbon dioxide, it might process silicon dioxide, essentially sand, and exhale something like silane gas. Such a creature would likely thrive in environments that are far too hot for carbon-based molecules to remain stable, perhaps on a world much closer to its star. Its metabolism would be slower, its biology more rigid, perhaps resembling crystalline structures more than soft, cellular bodies. The potential for exotic biochemistries doesn't stop with silicon. On a cold, icy moon or a distant super-Earth like Proxima Centauri c, where temperatures are perpetually frigid, life might use liquid methane or ethane as its solvent instead of water. In such a cryogenic environment, the chemical reactions of life would proceed at a glacial pace, leading to incredibly long-lived, slow-moving organisms. Their cells might be built from lipids and other molecules that remain flexible at temperatures where water is frozen solid. Alternatively, in the dense, high-pressure atmosphere of a gas giant or a mini Neptune, life might not be surface-based at all. Floating, balloon-like organisms could drift through the clouds, feeding on chemical nutrients in the air, their life cycle entirely aerial, never knowing a solid surface. This speculative exercise is more than just science fiction. It is a crucial guide for our search. If we only look for life as we know it, we risk missing life as we don't know it. Our instruments, like the James Webb Space Telescope, are calibrated to detect biosignatures we understand, like oxygen and methane. But a silicon-based ecosystem or a methane-breathing organism might leave behind a completely different atmospheric fingerprint, one we haven't even thought to look for yet. The true key to discovery lies in maintaining this balance, using Earth's extremophiles as a starting point to understand the limits of biology, while keeping our minds open to the astonishing possibility that the rules of life are far more flexible and creative than we have ever dared to dream. While we search for the faint chemical whispers of biology in alien atmospheres, an even more profound question lingers. Could some of these worlds be home to minds that look back at the stars and wonder just as we do? This shifts our focus from biosignatures, the signs of any life, to technosignatures, the detectable evidence of advanced technology and intelligence. These wouldn't be the byproducts of simple metabolism, but the deliberate or incidental output of a civilization, a beacon or a footprint that screams someone is home. The very planets we've explored, from the balmy shores of TRAPPIST-1e to the enigmatic depths of K2-18b, become infinitely more compelling when we consider they might not just host life, but civilization itself. The classic and most enduring search for these signals is for narrowband radio transmissions. The concept is simple yet powerful. A concentrated radio signal at a specific frequency, unlike any natural astrophysical process, would be an undeniable sign of intelligence. For decades, initiatives like SETI, the search for extraterrestrial intelligence, have tirelessly pointed radio telescopes at stars like Proxima Centauri and the TRAPPIST-1 system, listening for any pattern or signal that stands out from the cosmic background noise. They are essentially eavesdropping on the galaxy, hoping to catch a fragment of a broadcast, a radar sweep, or even a deliberate message aimed at the stars. The sheer longevity of this search, spanning over 6 decades, is a testament to our deep and persistent hope that we are not the only ones trying to make our presence known. But the search has evolved far beyond just listening for radio waves. Scientists now cast a much wider net, looking for other potential technosignatures that an advanced civilization might inadvertently leave behind. One of the most fascinating ideas is the search for megastructures, colossal artificial constructions that could orbiting a star. The most famous theoretical example is a Dyson sphere, a vast swarm of energy collecting satellites or habitats that would encircle a star to harness its total power output. From our vantage point, such a megastructure would block a significant and irregular amount of the star's light, creating a unique and unmistakable dimming pattern unlike any known natural planet or dust cloud. While no definitive megastructure has been found, the mere act of looking for them forces us to contemplate the staggering engineering capabilities a truly ancient and advanced species might possess. Other potential technosignatures are even more subtle. We could potentially detect signs of industrial pollution in an exoplanet's atmosphere. Certain artificial chemicals like chlorofluorocarbons or nitrogen oxides have no natural production mechanism on a large scale and would stand out as glaringly artificial components in a planetary spectrum. Imagine the irony. Our first proof of alien intelligence might not be a welcome message, but the detection of their smog. Furthermore, we could look for the glint of artificial light on the night side of a tidally locked planet. The permanently dark hemisphere of a world like Proxima Centauri b would be a perfect canvas for the glow of cities, which would present a distinct spectral signature compared to the reflected light of its dayside. This expansive search is no longer confined to a few dedicated radio dishes. It is becoming a mainstream part of astronomy. Modern sky surveys, which continuously scan vast swaths of the cosmos, are now programmed to automatically flag any anomalous signals or strange light curves that could indicate artificial origins. The James Webb Space Telescope itself, while primarily a tool for studying biosignatures, could potentially stumble upon evidence of atmospheric pollution or other large-scale planetary engineering. Every new tool we build adds another layer to this grand investigation, increasing the odds that if a civilization out there is making noise, we might finally be in a position to hear it. The search for technosignatures is ultimately a search for companionship on a galactic scale, a hope that the silence of the Fermi Paradox is not an ending, but simply a prelude to a conversation that has yet to begin. This thrilling search for life beyond Earth comes with a profound responsibility, one that forces us to confront difficult ethical questions that extend far beyond pure science. The moment we detect a biosignature on a distant world, or even worse, consider sending a probe to one, we must grapple with the potential consequences of our curiosity. The overarching field guiding this caution is known as planetary protection, a set of rigorous protocols designed to prevent biological contamination between worlds. These principles are not new. We have been practicing them for decades with our exploration of Mars. Every rover and lander we send to the Red Planet is meticulously sterilized in clean rooms, with some components even baked at extreme temperatures to eliminate any hitchhiking Earth microbes. The goal is twofold: to protect any potential native Martian life from being outcompeted or destroyed by our terrestrial bacteria, and to protect the scientific integrity of our search. If we were to find amino acids on Mars, we must be absolutely certain they are not simply contaminants we brought with us from Florida. This concept of forward contamination taking Earth life to another world is only half of the equation. The other, perhaps even more spine-chilling consideration, is back contamination, the risk of bringing an alien microorganism back to Earth. While this sounds like the plot of a science fiction thriller, space agencies like NASA take this threat extremely seriously, developing elaborate quarantine procedures for any future sample return missions. The concern isn't necessarily a malicious alien plague, but rather an organism for which Earth's biosphere has no defense. An alien microbe might not be pathogenic to us, but it could potentially disrupt our ecosystem in unpredictable ways, outcompeting native species or altering soil and water chemistry in a catastrophic cascade. The meticulous containment plans for Mars samples, which would treat them with the same level of biosafety as the most dangerous pathogens on Earth, are a direct response to this sobering possibility. When we shift our gaze from Mars to the exoplanets on our list, these ethical considerations expand to a staggering scale. The question evolves from how do we avoid contaminating this rock, to should we ever make our presence known at all? This is the heart of the debate surrounding active SETI, or messaging extraterrestrial intelligence. While traditional SETI involves passively listening for signals, METI involves actively broadcasting powerful, targeted messages to stars like Proxima Centauri or TRAPPIST-1, announcing, "We are here." Many prominent scientists, including the late Stephen Hawking, have warned against this, comparing it to the foolishness of shouting into a dark and unknown jungle. His cautionary argument suggests that an advanced civilization capable of interstellar travel might not see us as intellectual equals, but rather as a primitive resource to be exploited, leading to consequences far more dire than simple contamination. On the other side of this debate are those who argue that hiding is both pointless and contrary to the very spirit of exploration. They point out that our television and radio broadcasts have already been leaking into space for nearly a century. creating an expanding bubble of information about our planet that any sufficiently advanced species within 100 light-years could detect. A deliberate, thoughtful message, they argue, is far preferable to our accidental transmission of soap operas and reality television. Furthermore, proponents believe that a civilization capable of crossing the interstellar void would almost certainly have moved beyond a need for conquest and resource plunder, and that making contact could represent the greatest moment of intellectual awakening in human history. This leaves us with a delicate balancing act for future missions. As we develop the technology to one day send tiny, light-sail-powered nanoprobes to our nearest exoplanetary neighbors, we must embed these ethical principles into their very design. A probe destined for Proxima Centauri b would likely be programmed to make a cautious, distant orbit, using its sensors to study the planet from afar without ever risking a landing that could contaminate a living world. Our thirst for knowledge must be tempered by a deep humility and a commitment to the prime directive of interstellar exploration: to observe, to learn, and to preserve the sanctity of other worlds, not as conquerors, but as respectful guests in a cosmos that may be filled with life we are only just beginning to imagine. And so our journey across 30 worlds comes to a close, a tour that has taken us from our very next-door neighbor, Proxima Centauri b, just over 4 light-years away, all the way to distant Kepler 1606b, orbiting a star thousands of light-years from Earth. We have encountered a staggering cosmic menagerie, super-Earths with crushing gravity and thick, insulating atmospheres, hycean worlds with global oceans hidden beneath shrouds of hydrogen, tidally locked planets with eternal daysides and icy nightsides, and tranquil, rotating worlds bathed in the gentle light of calm, ancient stars. Some orbit single suns, while others dance in the complex gravitational embrace of binary or even triple star systems. This incredible diversity is the most important lesson we have learned. The galaxy does not produce a single template for a habitable world. Instead, it offers a spectrum of possibilities, each with its own unique set of challenges and opportunities for life to arise. What unites these 30 extraordinary candidates, despite their profound differences, are the fundamental ingredients that scientists believe could make them livable. It begins with location, the fabled Goldilocks Zone where temperatures might allow for liquid water. But as we've seen, location is just the starting point. A world also needs the right physique, a rocky composition and sufficient mass to hold onto a protective atmosphere. That atmosphere itself acts as a global thermostat and shield, capable of warming a frigid orbit or cooling a scorching one. Crucially, the star must be a nurturing parent, providing stable light for eons rather than sterilizing flares. And perhaps most importantly, a planet benefits immensely from a strong magnetic field, an invisible force field that deflects harmful radiation and preserves its precious air. It is the delicate, beautiful interplay of all these factors: orbit, composition, atmosphere, stellar temperament, and magnetic protection that transforms a barren rock into a potential living world. This search, breathtaking as it is, has only just begun. The 30 planets we've explored are merely the first few chapters of a story that will span generations. Every new telescope we launch, every new algorithm we write, peels back another layer of the cosmic onion, revealing worlds more astonishing and wonderful than the last. The James Webb Space Telescope is right now analyzing the atmospheres of these distant points of light, and on the horizon await even more powerful observatories that will bring them into stunning focus. We are living in the golden age of discovery, a time when the question is no longer if we will find another living world, but when. The evidence is mounting that the cosmos is not a cold, empty void, but a vast potential garden, teeming with worlds where the conditions for life are not just possible, but perhaps even common. The greatest adventure in human history is unfolding right before our eyes, and you have a front row seat. Stay curious, look up at the night sky, and remember that around any one of those twinkling points of light, there could be a world with its own stories, its own landscapes, and perhaps its own eyes looking back out into the darkness. If this journey has sparked your imagination, make sure you subscribe so you don't miss what comes next. The next big discovery could be announced tomorrow, and we will be here to explore it with you. Now we want to hear from you. After touring these 30 incredible worlds, from the water vapor-shrouded K2-18b to the tantalizingly Earth-like Kepler 1229b, which one do you think holds the most promise? Share your pick and your reasoning in the comments below. Let's continue this conversation about our place in a universe that grows more amazing with every passing day.